Okay, we're going to cover this one now. So this is number 16, but it depends on the graph on the page to the left of it for both 14, 15, and 16. It's this one right here. The question is the nearest percent by what percent of the population of the United States increased from 1994 to 1998? But the information that they give us is relative to car thefts. So this problem is complicated as we discussed initially, and I apologize for floundering a little bit because I wasn't sure, I wasn't confident of where we were going, and I apologize, I just didn't know. So I did some research, and I want to give credit where credit's due. I have published up at the top here a little note for where I got this from. This led me in the right direction because they made a simplifying assumption that I hadn't made when we were discussing, and this simplifying assumption makes it a little easier. With that said, I'm going to go ahead and review some of what we talked about because it's going to be important in this problem. One of the first things that's important in this ratio problem is to create a relationship. This graph, and we talked a little bit about this, now I've kind of brought it to conclusion. This graph shows rate per 100,000 inhabitants and number of offenses known, and it shows the decrease. When we talked, I erroneously said, hey, it's the decrease year to year. It is year to year for each section here, but it's also talking about the total accumulated from 1994 to 1998 in the vertical section there. So just to clarify, from 1994 to 1995, there was a minus 4.3% number of offenses decrease, and total number of offenses decrease, excuse me, in the total population, and negative 5.2% decrease rate per 1,000 inhabitants. So that's useful, but then, for example, from 1994 to 1998, minus 19.4 and minus 22.4 here are the total accumulated difference. So we can just work our way down, and that will make things easier. Alright, now that we have that information, let's start talking about this problem. So how can we relate these two lines? Well, the total number of offenses, right, is this side, and this is rate per 1,000. So this is just a sample of the population, which is what's going to help us to solve for the total population, since they don't ever give us that initially. So for example, if we set up some sort of relative equation for 1998, kind of like we're doing online when we discussed this, right? I can say the total number of offenses or car thefts for 1998 over the total population for 1998 is some number of percent, okay? And then we can also say the number of offenses per 100,000, excuse me, people equals the same number of percent, because it's some sample of the population, okay? So this is what's going to help us, because we can set these equal to each other. Now, what it also means is that in order for there to be a difference in these changes of percents, that means our population must be increasing each year, okay? So that's the only way. So first of all, what I'm saying is, because these both equal the same percent, since this number of offenses per 100,000 people is a sample of this, alright? And this number of offenses known is this number, okay? And this rate, this whole percent, is this number. So that's going to help us out. And obviously what would be extremely beneficial is if they just gave us the population at any point so we could use that information, but they don't. So save that piece of information. It'd be a good point here to pause this to think about it, or copy down notes. I'm going to clear this out to transition on to the next part. that you will see in 1 second. So let me clear this out and we'll transition on to the next part. So I need to review something else that we talked about online. We also talked about online how when we're doing percent decreases, that as we do percent decreases, it's not as simple as just minus 19.4 times some numbers. So I'm going to recapture that conversation here. So let's talk about population increase first, because in my mind that's easier to understand than population decrease. So population increase is always the initial population times some percent growth, okay, equals new population. So for example, if we started with 100,000 people in any population and then we had an increase of 20% over some period of time, over 2 years, okay, it would seem easy to just take this 20% and put it in for our rate. So 100,000 times 0.20 equals our new population. But 100,000 times 0.20, right, is just going to give you 20,000, right? So this is not the correct way to approach this when you're trying to find the total new population. This only tells you how much it's added on to here, because the total new population is 120,000. So how do we do this in one calculation? Well, it's pretty straightforward. We say we want to include all of the original population and the new population. So the way we do that with a decimal is we say, instead of just 20%, we say it's 100% plus 20%, okay, which equals 120%. Now, if we redo this formula right here, we can do 100,000 times the decimal form of 120%, which is 1.20, equals, and that you can clearly see is going to give you 120,000, but just for demonstration, right? 100 times 1.2 equals 120,000. So that's population growth, okay? Again, we can pause it here if you want. I'm going to clear this out and now go over population decrease, which is what we deal with in car theft in this problem, but overall we have a population increase. So let's talk about decrease. So again, if you start with 100,000 people and you say that you have a decrease of minus 20%, okay, loss over 2 years, right? Again, it would seem reasonable to infer that, oh, we just take this times negative 0.20, converting this to decimal, but that does not give you what your new total population is, okay? That doesn't give you that, right? That's not what it gives you. What it gives you is actually just how many people were lost or died or moved or whatever the case. So for example, 100 times 0.2, right, equals, or excuse me, 100 times 0.2 negative, right, equals minus 20 in this case, 1,000. So to get our new total population, we'd add this to this, right? So 100 minus 20,000 equals 80,000. So that's our new total population after we've lost some populace, right? Okay, so how do we do that in one algebraic equation? Well, for example, just like previous, we say we want to use the original 100,000 and take away what our lost amount is. So we just take 100% and we add the loss of population, which is negative in this case. We minus 20%, which equals 80%. Now convert that into decimal and use that as your rate. So you take your initial population times 0.8, that's this as decimal, equals, and that will give you your new total population. So 100 times 0.8 equals 80,000. Okay, here's another good place to pause. So I talked about the general relationship between these two form equations, the graphs here, and then I talked about percentages, both increase and decrease. Now we're going to finally get to the problem. So when we were talking online, I was trying to solve it just by brute force algebra. I don't know if I would have gotten to it, but the website that I mentioned to you earlier and I had posted here gave a good idea. They said, why don't you just make a simplifying assumption and just guess at what the initial population is, and make it something easy, which I hadn't thought about that. And so basically just by plugging in a starting point, we have a place to start with real numbers. So, for example, we don't know what our initial population is in 1994. So we'll use a nice round figure. We'll say, what if our population is 100,000? Boy, that's nice, because now that means our rate per 100,000 inhabitants is the same, right, as our total population. So our total population in 1994 is 100,000. All right. So then we also can make a simplifying assumption and say, let's use a nice round figure and introduce a number for the total number of car thefts that year. Again, I want to make it something like 10% of the population, or 10% per 100,000 inhabitants, since there are only 100,000 inhabitants, to make the math nice and easy. So we can just say, we'll say there's 10,000 thefts per the total population. This is total number of offenses. Okay, so that's this number right there. All right, so now we can remember that original equation I wrote up in the beginning. We can draw on that. We can say, well, then our total percent of thefts per total population that year is some amount, right? So we can just say the total population in 94 was 100,000, and the total number of thefts was 10,000. Well, that's nice, because now that we've used these nice round numbers, that lines up with our rate per 100,000 inhabitants, because that's theoretically all there was as a population. Okay, I'll explain why we can do this simplifying assumption in a little bit. So that roughly gives us a 10% car theft, right? So if I say 10,000 divided by 100,000 equals 0.1, or 10% car theft. Okay. Well, this is nice, because now we have the total population, the percent per total population, and the percent per 100,000, because I pretended that my population was 100,000 in 1994. All right. So now I can calculate out, I can extrapolate and figure out what is the number of car thefts per total population, or total number of offenses, in 1998. Well, they decrease by 22, let's see here, for the total population it decreases by negative 19.4%. Okay, so using the math we talked about before, that's a decrease over 4 years. So if I want to do the math to find out from 10,000 to down to how many total number of offenses there actually were, then I can't just take it times negative 19.4, right? I take 10,000 times 100% minus 19.4%, right, all as a decimal, equals the number of offenses for the total population in 1998. All right, so this is going to be the same as 10K times 100 minus 19.4, 80.6. So this is 80.6% here. Okay, so 80.6%. So now I just convert that to decimal. 0.806, and then I can finally carry out the multiplication here to find the number of offenses in 1998 based on the fictitious numbers we used. So, so 10,000 times 0.806 equals 8.06 thousand. So 8.06 thousand total number of thefts in 1998. So now we know our total population in 1994, the 10,000 total number of offenses in 1994. Okay, so this is all 1994. Now we also know the for 1998, based on these fake numbers, the total number of offenses for the whole population. So 8.06K. Alright, now we need one more piece of information here in order to find out what the population actually was in 1998, and we can relate it per 100,000 inhabitants. So this would be a good place to pause. I'm going to clear this out, the bottom pieces of information. Alright, so now let's use the same process to find out the number of, right here, thefts per 100,000. Right? In 1994, it's 10,000 per 100,000 because we chose a nice number of 100,000 total population, right? And eventually we're going to find this number, the total population in 1998. Alright, so now we have we're working our way to everything we need in the problem. So we need to find this number right here. We need to find out what is the number of thefts, or percent, excuse me, percent of thefts of offenses per 100,000 people. Okay, so we're going to find that out. So we just simply take the known number of thefts per 100,000 people in 1994, again, times the change per 100,000 inhabitants, which is negative 22.4 this time. So again, 100%, it's a decrease, minus 22.4% is going to give us our number per 100,000 inhabitants. Okay, sorry, some of the writing is chicken scratches here. So 100,000, 100% minus 22.4 is 77.6. So 77.6%. That's the result of this math. So convert that into a decimal. 10,000 times 70.776 equals 10 times 0.776 equal 10 times 0.776 equals 7.76 thousand per 100,000. So now we know this number also, 7.76 thousand. So finally we can set up, using that initial equation, the relationship between the total population, the per 100,000 versus per total population. So here's a good place to pause it if you need to catch up with the numbers. So let's set up that final equation. Alright, so we don't know the total population in 1998. That's this number. Okay, we do know the total number of thefts for the total population, which was 806 8.06 thousand. Okay, and we do know the per 100,000 inhabitants total number, which was 7.76. Okay, so now we can just cross multiply, because here's our ratio for this number, right? This right here is 7.76 thousand car thefts per 100,000 people. That's this right here, right? That's why we used, a second ago, we used negative 22.4 to find that. Now, the total number of thefts for the entire population is more than per 100,000 because the total population is a lot larger. Okay? So, we can find that information here. All I'm going to do is cross multiply. So I take this side times 100, take this side times 100. That's going to divide out. That's going to give me 8.06 times 100 equals obviously 806. So this becomes 806 per total. Okay, population in 1998 equals 7.76 thousand. Okay, so the K always represents thousand. So now I'm just going to cross multiply by this number on both sides. So total on this side is going to divide out total on this side. Finally, we're at a place where I can just divide this number by this to get my total population. So 806 divided by 7.76 equals 103. So 103.86 thousand in 1998 is my total population in 1998. So 103.87 I'll say, because it's 103.86. So that's my total population. So now we have this number up here. Finally, we've kind of bootstrapped our way up to it. So 103.87 thousand, okay, is the total population in 1998. So you can see that from our assumption of 100,000 in 1994 to 1998, now the population is 103.87. So there was some percent growth. So now we can find that percent growth. So the percent growth is the easier part. It's just the initial population divided by the new population. And that will give you your percent growth. So this was the initial population we plugged in, a simplifying assumption to make this problem more doable than using just algebra terms. And then here's the calculated new population based on the original assumed population. So I'm just going to take 100,000 divided by 103.87 thousand. Oops. I think I might have those backwards, sorry. Oh, one mistake. Sorry, I flipped these numbers. I apologize. So let me clear that out. 103.87 by 100,000. Okay, now this will give us our percent growth. So 103.87 divided by 100 equals 1.0387. So 1.0387 which converting that to percentage is 103.87% total growth from initial to new population. Well, to find out how much percent increase, right, we just take, instead of adding 100% like previous, we subtract 100%. So all of that finally will equal 3.87%. Finally, that's your growth. And that is, now you can round that to one of the closest answers. Now, to be honest with you, on a GRE, I would leave this question definitely till last, because the amount of time this would take to calculate all this and sources of error are substantial, and this is definitely reaching higher level of computation. So if you have any questions, let me know. I hope this helps.